Okay, fall storms recently dropped, let's say, 4 centimeters of water on the city. Um, Over an area of just 50 kilometers square, this could correspond to 2 million cubic meters of water, which must be drained to the river or to Lake Erie in a reasonable time to prevent flooding, right? So a particular sewer line must handle 1.56 meters cubed per second in order to accomplish this. And let's say it's a sewer line that runs down like if you're familiar with the west side of Buffalo, like Ferry Street runs right down to Black Rock Canal. And we want to know is what is the roughness required to do this? So the length of this is 2 kilometers. The change in height is 10 meters. The diameter of the sewer pipe is 1 meter, and there are two 90-degree bends in the pipe. And those 90-degree bends basically help it go uh, underneath the Black Rock Canal to get to the sewage treatment plant on the other side. So if we imagine it, this piping system then would look something like this. It comes down slowly and then down and over like this, where Black Rock Canal, so here's the road, like this, and then there's a bridge, here's the canal, and it ends in the sewage treatment plant on the other side of the canal. So yeah, and so here are our two 90-degree bends and our total distance of 2,000 meters of sewage treatment pipe. So let's solve this. So we're going to assume, just like we do for every conservation of energy problem, steady state. We're going to assume uniform properties, and we're going to assume, yeah, that's it for now. So equations, we're going to use our conservation of energy equation. We have P over rho G plus V squared over 2G plus Z out, is equal to P over rho G plus V squared over 2G plus Z in plus H pump minus our sum of all of our head losses. And remember, we're doing the minus sign here because in the book, none of the minor loss equations are negative, and we know that if it's a loss, we have to take it out of our system, our energy out of our system, so it has to be a negative sign. So let's simplify our equations here. We're going to draw our control volume such that we kind of come up to the top of the road, come through our sewer pipe, and then end in whatever catch system that they have at, and it's actually a big tank. If you look at them, they're large tanks that they use to deal with all this stuff. So we're going to come up and go to the surface of the water in these tanks here. So these tanks are open to air at the top. Let's assume gauge pressure over here. So all our pressures are equal to 0 for our pump, for our control volume. Our velocity at our entrance and our exit is going to be 0. And we have a Z in is equal to 10 meters. Z out is going to be equal to 0 because we're going to draw our control system such that, coordinate system such that it's 0. And yeah, we have no pump in our system, so H pump is equal to 0. And now we just have to worry about our head losses. So let's look at that. We know that we're going to have a major head loss for our entire length. So our sum of our head losses is going to be equal to an F L over D V squared over 2G. We have to figure out our F. We have to figure out our V. We don't know what our V is inside of our pipe. Remember, inside of our pipe, our velocity is cannot be neglected. At the surface of our entrance and our exit, it can, though. It's a little bit confusing there. And this is going to be equal to adding to it 2 times K 90-degree bend times V squared over 2G. and this is the velocity again inside of our pipe. So we need this velocity. So if this is equation 1, equation 2 is going to be V is equal to Q divided by A, which is equal to 1.56 meters cubed per second divided by pi times 1 meter squared divided by 4. So our velocity ends up equaling 2 meters per second. Good. And yeah, so now we know our velocities, we know our L, we know our D, G, we know our K90. We can look it up. In fact, let's go look it up now. Go in your book and look it up. And when you look up a 90-degree bend, you find out that our K is going to be equal to 0.3, which is a lot. And the only thing left to do is solve for our F. So when we plug stuff in, we find out that 0 is equal to 10 meters plus, excuse me, negative F times 2,000 meters divided by 1 meter times 2.0 meters per second squared divided by 2 times 9.8 meters per second squared plus 0.3 times 2.0 meters per second squared divided by 2 times 9.8 meters per second squared. And so we can solve for F, and when we do, we find out that our friction factor has to equal 0.0242. And now we have to go to our Moody chart or to our equations and kind of use them in a different way. Normally we know our Reynolds number and we know our E over D, and then we solve for our F. Now we know our F and we know our Reynolds number. In fact, let's go calculate that now. Our Reynolds number is equal to rho VD over mu. We know everything in this. We know the density, the diameter, the viscosity, and the velocity. I missed an opportunity here to find out the average density of sewage. I'm going to assume it's pretty close to, in a rainstorm, it's going to be pretty close to water. So we're going to leave that 1,000 kilograms per meter cubed. And this ends up being equal to 2 meters per second times 1 meter times 1,000 kilograms per meter cubed divided by 1 times 10 to the negative third kilograms per meter second, or Pascal seconds. And our Reynolds number then is equal to 2 times 10 to the sixth, so 2 million. Excellent. So again, we have our Reynolds number, we have our friction factor, we don't have our E over D. So if you have your Moody chart now, what you would do is you would come over here and you would have, your E over D lines coming down like this. You would go, just like before, you would go up on your Reynolds number, but this time you would find your friction factor and you'd go over until you have an intersection, and then you would follow the shape of the E over D down until you come over here and you would read off, you'd estimate what your E over D is based on how spaced it is between known E over D lines. If you have your implicit equation, it's no different than before. You just plug in the things you know and solve for your E over D. Same with the explicit equation. So go ahead, figure out some way to do it, figure out one of the 3 ways, solve for E over D, try it maybe multiple ways, see what happens, and then hit play again. Okay, I'm assuming you did that. So E over D then, if you solve for it, ends up being equal to 0.002. So that's equal to E, our roughness, divided by our diameter, which is 1 meter. And so our roughness then is equal to 0.002 meters or 2 millimeters, which is pretty rough. An old sewer, if you look it up, people have done this measurement. Epsilon, our roughness for an old sewer, is equal to 3 millimeters. So this is a pretty old sewer line that we're looking at, and a E for a new new smooth concrete sewer line is equal to 0.025 millimeters. So clearly we're getting a lot of losses in our sewer pipe, which means and it's because our roughness is so large, right? Things get stuck to the sides, and it's really gross and really, really inefficient. So there's a reason why they have to go through and they scrape the walls of sewer pipes. Also because as things accumulate on the walls, your diameter decreases. And we've seen how important the diameter is for maintaining high flow rates. Even a small change in diameter can really, really hurt you because your velocity increases. And yeah, lots of reasons, right?